Back in the good old day of exponentials, we had a graph where we did f of x equals 2 to the x. And that was nice. We were able to get a little xy chart, right? We did 4, 3, 2, 1, 0, -1, -2, -3, -4, where we put in these guys as exponents. And we got out numbers big like 16, 8, 4, 2, 1, 1/2. 1/4, 2 to the -2. 2 to the -3rd power is a 1/8. 2 to the -4th power is a 1/16. So we put all those guys in and we got it out, and the graph looked like this, where we had the point 0, 1 always on every exponential, whether it's a 3 or a 1 or an 8 or a 5 or whatever, and then it shot up exponentially and there was a horizontal asymptote. We were also able to note that the domain was all real numbers, and the range we only hit where y was bigger than 0. We never hit negatives and we never got down to y. So now let's take and see what happens if we were to draw the inverse of this thing. Okay, so first of all, we would take and exchange the y and the x places. So we'd have something where we went x equals 2 to the y. And our xy plot, switching the x's and y's, would have, if we stick in 16, we better get the exponent 4 out. Notice how here we stuck in exponents, got out numbers. Here we're sticking in numbers and finding out what exponent we would have to get. So if we stuck in 8, we better get 3. 4 is a 2, 2 is a 1. A 1 is a 0. So whatever this new inverse function is, it looks like that. And if we stuck in a 1/2 little fraction, we start getting negative numbers. -2, 1/8 is a -3, and 1/16 is a -4. Okay, so this is very interesting. If we do the inverse of this exponential, we get this. And what does the graph look like? Well, the graph is this point gets reflected. It used to be 0, 1. It's now 1, 0. And instead of a horizontal asymptote, instead of shooting out there, it's going to shoot down here. And it's going to come up and shoot off that way. Now notice that the domain of this thing is only x is bigger than, not equal to, don't you put that in, 0. Now notice on the exponential, it comes down and never hits 0. So that means if we're doing the inverse, the opposite of this, we can't stick in any negatives because negatives were never hit over here in the original function. But on the range, look at how the arrows go down all the way and up all the way, just like these guys went left and right all the way. So that's going to be all real numbers. Wow! This is the inverse function. Look, we can see points, we can see a whole bunch of other things, the graph, the domain, and the range. What's it called? Well, y, if we try to solve for y, how do you get y out of the exponent? Y equals the exponent to which we raise 2 to get x. Okay, great, there's the function. So if we stick 16 in for x, this is the exponent to which we raise 2 to get 16. We get 4. Bingo, we solve for y. This is where, this is what it is. This is how we write it. Log base 2 of x. So these two mean exactly the same thing. And so when we do a function of logs, it already inherits a whole bunch of stuff with it. For example, we know that the domain of this function is everything bigger than 0. So we have to look at that. You can only take the log of positive numbers. 2 to this power, log base 2 of 16 is 4. Log base 2 of 8 is the exponent 3. And we already know what the range is. And we always know that log base anything of 1 is going to be a 0. That's important right there. So we can actually move this guy around as well. But let's take a break right now and make sure we understand a little bit of the logs that happen with normal numbers. So here we have just a little bit of these things. So log base 64 of 4, this is 64 to what exponent would be 4? And if we look at this right here, 64 to the you would have to cube root it. So that is the exponent 1/3. Let's put that in there, 1/3. Log base 144 of 12, you would have to square root it. So that's the exponent 1/2. Log base 8 of 512. So 8 cubed is 512. So that's the exponent 3. Log base 2 of 1 over 256. Let me see, 2 to what power equals 256? 8. So it would have to be a negative 8 power. When we stick in really small fractions, we're going to get out negative exponents. Remember that happened? Negative exponents on the exponential gave us very small fractions. So log base 64 of 16. Ooh, this is going to be tough. So 64, we would have to cube root it to get it down to 4 and then square it. So this is 64 to the 2/3 power. Yeah, cube root and then squared would get us 16. 7 to the 2nd power. 8. Oh, shoot, 8 to what power equals 32? We would have to cube root it to get it down to 2, and then 5th power it up there. 10 squared. 9 to what power gives us 9 cubed is 729, but it's a fraction, so that's negative 3. 9 to the negative 3 power equals 729. Let's write that out here so we can kind of see what that looks like. 9 to the negative 3 power is 1 over 729. So that's really what we're finding is the exponent. Log base 11 of 0. No, log base 11 of 1 is 0. And we saw that anytime you stick in 1, you'll get the exponent 0. This would be 6th root, 8th power. If you're doing a 2, oh, we could do something even better than that. That reduces down to 4/3. That's right. If we cube root 64, we get 4. And then we 4th power it, 4/3. Log base 6 of 216, that's just a 3. Log 28 of 1, that's a 0. That's a negative 2. 2 to what power is 16? That's a 4. 8 to the cube root, 1/3 power, is 2. 25 to 125, we would have to square root it to get it down to 5, and then cube it to get it up to 125. Can you kind of see how that works? Filling out all of that thing, the log monster, will get you a clear picture of how a log is an exponent. If logs are exponents, then this thing, the rules are going to be exactly the same. You remember the rules of exponents? Let's write them over here. We had this one, x squared times x to the 5th. We add exponents. We had x squared to the 5th power. We had x to the 10th. We had x to the 5th over x squared. That was x cubed. We subtracted. And x to the negative 3rd power is 1 over x cubed. That was a negative exponent. And x to the 0 is always 1. So in logs, this is what happens. If you have log, base anything, it could be a 2 or a 7, and you're multiplying these, their individual exponents will add. Multiplication in the bases here will allow their exponents to add. So this actually is the first exponent plus the second exponent. And it's exactly the same as this right here. And so let's do that with a number just so you can kind of see that that indeed works. If I have 2 squared times 2 to the 5th, we got 2 to the 7th. And we saw how that works. This is 4 times 32 is 128. It actually works. So let's try it again. If we had log base 2 of 2 squared times 2 to the 5th. Now, we know that this would be log base 2 of 128, which is log base 2 of 128. That's to the 7th power. So this better equal 7. Well, notice with this multiplication, you can do log base 2 of 2 squared plus log base 2 of 2 to the 7th, 2 to the 5th, sorry. And notice what happens. Log base 2, logs and exponentials are inverses. And this is the crucial thing. They undo each other. That's 2 plus 5 equals 7. That's exactly what happens. This is log base 2 of 4 plus log base 2 of 32. And yeah, 2 plus 5 equals 7. It's the addition of the exponents. So let's look and see what that means over here. This is log base b of something to some power. Well, that means that this exponent, p, can times the other exponent, log base b of m. And it works. You can actually move that out in front. Subtraction. log base b of m over an n. That's going to be the top exponent minus the bottom exponent. There we go. Negative. Yeah, what happens with a negative exponent? Well, yeah, it's just 1 over it. This is kind of fun. If we have log base b of, let's say, something like 1 over n, that's, according to this rule up here, log base b of 1 minus log base b of n. Now, I'm going to do something right here. I'm going to jump to the next rule really quick. Log base b of 1 equals 0. That's anything to the 0 power is 1. This guy is 0. 0. Yeah, see how that guy goes away? Yeah, if you have a reciprocal, it's the opposite of having log of n. These are all the exact same rules going backward and forward, and you get to expand and break them up and stuff like that. There are a few mistakes that come into being and that you have to watch out for. So the first one is if you have something like log base e, we write as ln of 5 or something like that. This is a function of 5. And if you do something like this, ln of 7, that is not the same thing as 5/7. These are not numbers. They don't cancel. They're functions, and you can't just do that. Particularly if you have ln of 5 over 7. Using this rule over here, it's ln of 5 minus ln of 7. That's the correct rule right there. But this, some people try to take, oh, that's ln of 5 over ln of 7. That is not the case. It doesn't distribute and it doesn't cancel. This would be something that you'd actually stick in your calculator. Make sure that we understand e to the 0 is a 1 all the time. X to the 0 is always a 1. And then you'll see a lot, natural log of 1, that is always 0. And these are equivalent statements. So log base e of 1. So this always connects up to this point right here. Natural log of 1 is 0, and e to the 0 is always 1. It goes through whether you have an e or a 2 or a 7 or a 15 as a base. The other thing, some people will do this one incorrectly, and they'll try to factor this out and write this as log base b of m plus n. And that is not the case. It doesn't distribute. It doesn't go into the parentheses like that. These are the appropriate rules on how you would be able to expand logarithms. As one final thing, let's make sure we cover how to graph and move these guys around. So if we had something like f of x equals log base 5 of x minus 4 plus 3, something like that. Notice that we are a function. These both are going to be functions passing the vertical line test. A couple of things that normally would happen. Let's take and change just a couple of these so we can see the colors that we're going to use here. There we go. Now we have x minus 4 in blue and plus 3. So log base 5 of x, it's going to be, there's a standard point that we always know, and that is 1, 0. That's the normal log x. Remember, as a vertical asymptote right here at x equals 0. And the domain is normally just x equals 0. And this point that we're going to watch is 1, 0. And this could have been log base 2, log base 5, or ln of x. Wouldn't have mattered. Now, it moves it 4. What does the blue do? Moves it 4 to the right. And so over here at x equals 4, this is now going to be a vertical asymptote. And we go through this point. Notice what it just made our domain look like. Our domain is now going to be the set of all numbers such that x is bigger than 4. You can't stick in smaller numbers. If you stick in 3, you get 3 minus 4 is a negative 1. Try to take the log of a negative number, you don't get anything real. So there's how you do the domain. If you'd like to do it in slow motion, you say x minus 4 is greater than 0. That's what you have to make bigger than 0 is whatever's inside the log, and then you solve it and it gives you your domain. The range is still all real numbers, and so that's pretty good. That's nice. Is still, oops, the range is going to be all real numbers. I wrote that backwards. But then we're going to add 3. So this point right here, which is now 5, 0, is going to go up here to the point 5, 3. We watch him move as it went 4 that way, still vertical asymptote, and still heading off that way. So there we go. That's how we do graphs.